Let's start again. So the next speaker is myself. Okay. So I'm going to talk about effective fibrations in simplicial sets, which is some joint work I did together with Faber. I started doing this when he was a PhD student in Cambridge, but he now works for the European Central Bank. But we're still thinking about these things. So the motivation for this work is very similar to what Nicola also discussed in his previous talk. We're also the back of what we have at the back of our minds is well, two things. So what we have in the back of our mind is really homotopy type theory. So the idea of homotopy type theory is in a way that it should bring together two things. So it brings together on one hand things from homotopy theory, and on the other hand logic and type theory. And it is all based on, which also I think includes questions concerning so type theory is a formal system which can act as a foundation for mathematics, constructive mathematics in particular. But it is also supposed to be a computational framework. So everything that we write in type theory should be the idea is that it is also a computer program and can be executed. So questions of computation are also very important, I think. And so for that reason, the questions that we look at, like concerning effectivity and constructiveness, are very much at the top of our minds. So the idea really is of this whole area of homotopy type theory is that we want to interpret types as homotopy types, or you could say infinitive groupoids spaces. So the idea is that, so this is a kind of an unexpected interpretation for how we think about this notion of a type in type theory, and it has led to a lot of work. And it has many sort of benefits. For instance, one of the things that we already talked about is that this point of view leads to a new interpretation of the Martin's identity types in type theory. They can be thought of as path spaces. They lead to new axioms like the univalence axiom. They lead to new construction principles like higher inductive types. So that in that sense, it is a very sort of fruitful idea. Also, that as seen, for example, in the homotopy type theory book, it has led to all kinds of new ideas about propositions and sets, how to think about these notions in the context of type theory. So one question, of course, always is that it is having this idea is nice, but can we make this precise? In particular, can this really lead to precise semantics for type theory? And that is, I think, why we care so much about Volotsky's model in simplicial sets. But Nicole also mentioned, because the reason why this is important, this gives us a semantics of type theory, in which types are interpreted as infinity proof voids, in particular as so basically this model makes clear that this is not just an intuition that we have, but it can really be made precise as a semantics for type theory. So as Nicole also mentioned, I mean, one of the questions that people immediately raised was, okay, so is the proof of this constructive? The answer is, well, not really. So this is based, very much based on the computer model structure. Simplicial sets. And the proof of that already is, I mean, is not constructive, it's not effective. There are all kinds of reasons for this. I mean, one particularly bad aspect from the constructive point of view is the theory of minimal fibrations, which is highly ineffective. Benno Nicole also hinted at there are questions about decidability of degeneracy. So for instance, I mean, that means, so we have, I mean, we have the idea, I mean, in textbooks, create the impression that simultaneously every object is cofibrant, and at the same time we have the generating cofibrations being given by these boundary inclusions, and constructively this combination of things is problematic. I mean, if you really believe that as a constructivist that these boundary inclusions are a set of generating cofibrations, then you end up saying something like, well, only those objects are cofibrant if they have some like decidability of degeneracy. So there's a bit of a tension there. So these are some aspects of the theory which are problematic from a constructive point of view. So I think all of us are basically trying to avoid the theory of minimal fibrations entirely. And what, for example, Nicola did in his previous talk is that he kept this idea, but he dropped that idea, which is one option. So all this is constructively difficult. So you could say, okay, well, I'm not a constructivist. Why do I care? So I think to that, I think there are basically two possible answers that you could give. On the one hand, if you care about the fact that type theory is supposed to be a theory of computation as well, then the fact that you have, I mean, and maybe you want, for instance, you want to compute with all of these ideas that all of these axioms and principles that Wygotsky suggested, like the univalence axiom or high inductive types, then you need some sort of computational interpretation for these principles. And if you perform this whole theory in a highly ineffective meta theory, it is unclear what the constructive computational interpretation of these principles should be. So that is like so there are all kinds of questions of computational significance, which can basically come up here. Another sort of motivation that you could have is you might want to do this, build, for example, this model structure over a category which is not sets and does not satisfy all the principles that you have in the category of sets, but rather maybe rotating tuples or something else. So you may want to build structure over elementary tuples with the natural numbers object, for instance. So I think both in our approach and in Carlos' approach, I think we can do with something less, even less than this. I think in our work we need something like a Cartesian closed category with finite coordinates. Should be enough to do at least what we are doing. So that is one other motivation for this. So the idea of this model structure really is that we want, or this model is that the types are interpreted as count complexes, and the dependent types are interpreted as the count fibrations. So one thing that you might want to have, and that's not a problem for in a constructive setting, is what I refer to as the DCP obstruction, after Basin, Copan, and Farman. So that says that the statement if A and B are count complexes, then so is A to the power B is not constructively valid. So one thing you can use, one thing that holds in the classical theory is that you want to build an exponential a to the power b, and this will be calm as soon as a is calm. With a classical result. However, that is not constructively valid. Not even if we assume that b is calm as well. So that result fails. Now, from a type theorist, this is really bad because, at least, we definitely want our model of type theory to have something like function spaces. And the natural thing to expect is that we can interpret these things using the exponentials in the category of simplicial sets. So we would definitely expect the count complexes to be closed under exponentials. So for building models of type theory, this is a real problem. And I think it is this problem which basically convinced the community that they should switch away from simplicial sets and move towards cubical sets. So I think in Nicola's work, you basically change the interpretation of the exponent, the function types into something which is not quite the exponential, I think. Or you take some cofibrant replacement somewhere. Yeah.
You need to replace with an assumption that A is cofibrant, B is
cofibrant. But then the cofibrant complexes, are they closed? They're not closed under exponential types.
Yeah, so you need to take the cofibrant replacement with the exponentiation.
Yeah.
It's not exponential anymore.
Right. Yeah. So, so basically what we try to do in our work is basically get around this fact. So yeah, so whereas Nicola basically takes the cofibrant replacement, we basically want to have a notion of a Kahn complex such that this statement is still constructively valid. And the idea is, so that this has come up several times already sort of in the workshop, is that we basically want to enrich the notion of a Kahn complex. So instead of saying that a Kahn complex is something which has the right lifting property against all inclusions, we want it to be a sort of a richer notion of structure. So it will still be defined by some sort of lifting property, but this lifting property is more complicated than what we see in the classical theory, and that is what we will call an effective configuration. So basically, so our goal is to find a nice structured notion of configuration and complex. Such that sort of what these effective configurations are. Such that well, eventually we want to have, ideally we want to have basically a model structure on simplicial sets based on this notion of effective configuration. Maybe something like an algebraic model structure. That is not how, I mean, that's not how far we got. I mean, we have something less, very less in a way. We basically have a model of some sort of type theory with pi sigma types, natural number types, 0 and 1, and a few things. But one thing what we do have is, in particular, is that we managed to get around this BCP structure. So what we can show is, first of all, well, let's say that the effective Kahn are closed under more generally effective configurations so that is a statement that if I have two configurations here, then I can take the push forward of this configuration from that configuration, so that's the right adjoint to pullback, and I get another effective configuration here. So that is for the types. We get an interpretation of type types. Secondly, we want the existence of universal effective conformations. So I don't want to say too much about that. So basically what I mean is that, I don't know, if we fix something like, I don't know, some regular cardinal or something like that, we can look at those configurations whose fibers are sort of bounded in size by that regular cardinal. And then what we want is that, we can call those things small, that there exists one particular small effective configuration such that any other effective configuration is a pullback of that one. Now this, so this is for the type theorist, this is related to the existence of universes. So this is also very much motivated by considerations that have to do with the existence of a model of type theory. This follows from a property of the effective configurations Okay, I want to explain what I mean by that. And finally, what I want is that classically every effective configuration and vice versa. Now that sounds a bit silly, but it is not so silly until you realize, as soon as you realize that these effective configurations are like a property, sorry, like structure. So what I really mean is that every map which can be equipped with the structure of an effective configuration has to be a configuration. That result is constructively valid. But it's the converse that is problematic. So constructively. So what I want is that in a classical matter theory, every map which is a configuration can be equipped with the structure of an effective configuration. Classically, every map which has the property of being a configuration can be equipped structure of so this is, I mean, ideally, as I said, ideally we build a model of homotopy type theory in simplicial sets using these effective configurations. Ideally, we build something like an algebraic model structure on simplicial sets based on these effective configurations. That is not how we got. The only thing that we really have is something which satisfies these three requirements. And I think right now, the notion that we have is basically the only notion which exists in the literature which has these three properties. So, so there are the uniform configurations of like Benno and Sumter. They satisfy properties 1 and 3. I mean, Benno also mentioned in his talk that by sort of thinking of configurations as structure rather than a property, one can regain the Frobenius property or closure and locus forwards, but their notion is not local in this sense, and which means that we do not know how to build universal uniform fibrations. Means that we do not know how to build universals using that notion. Okay, questions? Yeah.
What's the importance of the cardinal being regular in showing the universality?
I just wanted to say fix something.
Okay.
You mentioned the notion that satisfies 1, 2, and 3.
Yeah.
But it's not known if it gives rise to a model structure.
Yeah. Yeah, that's correct. Yeah, so I mean, one thing we started looking at this equivalence extension property, and we got a bit stuck. Look at it again. I'm not sure that it is impossible, but it's definitely more complicated than. Okay. So what do I want to do in the next half an hour? I want to give you a definition of an effective configuration in our sense. Now, if you look in our paper is really quite thick, and it contains, I mean, one part of the paper is that in the paper we give actually several equivalent definitions of what an effective configuration is. And many, I mean, so basically, you often use different definitions to prove different properties. So for this showing this particular property, it is most convenient to use this particular definition. And then we have a proof saying, okay, these definitions are equivalent. What I want to present to you is that what I think is the most beautiful definition. Is, and it is the one that we use to show property number 1. Okay, it is maybe not the one which is maybe the most intuitive, but I think it's the most beautiful, and that's the one I like best. All right. So. So basically, the remainder of the talk will be something like towards the definition. So our definition, okay, well, we're not going to be able to, so it will take several steps. So step 1 is I define 2 algebraic weak factorization systems on the category of simplicial. So the first one, so I define what I mean by a cofabrication. So as Nicole also mentioned, in the classical theory, a cofabrication is just a monomorphism. Here, what we want to do is we want to impose some additional requirements which are like invisible to the classical mathematician. Nicole imposed 2, and I think I just want to impose only 1. So, so the definition is that a map, let's say a mono, is a cofabrication solution, I think that's fine. So one can show also in the constructive meta theory that this is like the left class in an algebraic factorization system. So one thing is that one thing we hope that if everything works out, this will have the advantage that every object is covibrant. So trying to keep every object covibrant and not really speaker. So so this is okay. Now, I mean, maybe I should say two auxiliary algebraic factorization systems, because neither of them actually defines the class of effective configurations. So the second class, so the next step is I define an algebraic factorization system on simplicial sets whose left class we call hyperdeformation retracts. DRs. So the name is meant to suggest that they are like deformation retracts. They are like strong deformation retracts. Actually, they're even stronger than strong deformation retracts. So that's why we chose the name hyper deformation retracts. Okay. Okay, so this uses the existence of a kind of simplicial more half objects. And on simplicial sets. So this object, this M, so this was defined earlier by myself and Richard Garner in a paper. And actually, it turns out that it was actually defined before us in a paper by Berg. Actually, so it is a kind of, yeah. So let me see, how much time do I have to explain what it is? The idea is that it is like a path object. It is like a more path object in the sense that we have a strictly associative and unital composition. So one of our contributions also is that of our paper is that the definitions that are given in our paper with Richard or in the paper with Berger, they are kind of involved. So one of our contributions is that we give a simpler definition of what this M is. So it actually turns out to be an instance of a polynomial functor. Actually, that turns out to be quite useful as well for many of the calculations. So what this M gives us is M. What are the properties of M? M is an endo functor. Fullbacks. There are natural transformations. And the identity, there's like a source and a target map. There's identity map, and there is a map. So this is very much supposed to sort of suggest, so there is such a more path object functor on the category of topological spaces, where we, instead of just looking at paths of length 1, we look at paths of arbitrary length. This defines, I mean, this basically gives, I mean, if you think of X, yeah. This basically gives every topological space the structure of of an object of objects in a kind of internal category of topological spaces, where this is the object of arrows. And we can do something similar in simplicial sets. So basically, we can give every simplicial set the structure of the object of objects of a simplicial category, if you want, where M of X is the object of arrows. And then there is also the contraction. It's like something which contracts paths. Yeah, so at that time I can say something more about this more function. People are interested. Say more about the more function. So in fact, you can show, which I already did, I think, that if you have any category, say with finite limits, you have an endo functor preserving pullbacks, there are these natural transformations, there is a contraction with some more properties. There will exist an algebraic factorization system on your category. Then, given such an M, and find an algebraic factorization system in the underlying category. Where, yeah, so the idea is quite, I mean, absolutely standard for people in algebraic topology. We just take a map from X to Y and how do we factor it. I just want to say what the underlying factorization is. So we say we go to X times. Factorization using the vibration. Actually, there exists a more path functor on the category of categories, which is just given by sending x to the power 2, the arrow maps and the right maps for this, you get the, I think you get the growth fibrations and the split reflections. Split growth fibrations and the split reflections. So actually, that is an instance of this sort of more general. Yeah. So in general, you can say so a left map for this algebraic factorization system is a map I from X to Y such that, let's say, equipped with a map from I to X and like more homotopy in the right page from Y to M of Y such that some equations hold. So one composition identity, and the homotopy witnesses that the other composition is homotopy. Then it has to be not just a strong deformation retract, this H, but it has to be hyperdeformation retracts, and that is expressed using the contraction. So that gives you this axiom. So, I mean, in a picture, what this hyper axiom says is the following. So usually, so what's the idea of a deformation retract? You have one space sitting inside a bigger space, and then the inclusion. So for any point in the bigger space, or any point in the big space, there is a path going to a point in the smaller space. So continues. Starting point. Now, what this axiom basically tells us is that suppose we have this point here and we have this path going all the way here to this subspace, then if you take any point on this path, there is, of course, for this point, there is also a path going back to this subspace, namely sort of this bit of the path. And this axiom basically says, yeah, that is the path that is chosen by the deformation retract. And that, of course, in a sense, only makes sense because we're looking at paths of variable length. So I think this only makes sense sort of in the Moore philosophy. So clear?
So
Yes.
So that's like saying that you have your split epi,
Yeah.
and then you have your homotopy,
Yeah.
up at the top,
Yeah.
and that's contracted to the identity.
Well, I mean, this is stronger than just requiring that. I mean, this implies, but it is stronger than saying that the homotopy is just like the identity on the subspace. What it says is that if you have a path from any point in the big space to the small space,
okay,
and you take any point on this path, then what the contraction sort of chooses, the path that is chosen by the contraction is just this bit of the path. So that is that's what we call the hyperdeformation retract. So I'm moving clock now. And this implies, what is it? Something like after I equals R.
so this is the extracts here.
Yeah.
Yeah.
Yeah. So So for this particular Morpath, simplicial Morpath functor, there's a very important class of examples of these hyperdeformation returns. And so they're given by a face map together with an associated degeneracy map. Then the whole composition is the identity. So basically, this face map is on. So this part basically is a hyperdeformation for the particular more path we choose. So this is important source of examples. So there are some so there's, let's say, two important properties of hyperdeformation. The first property is that, okay, so they're the left class in an algebraic refactorization system, so the category of coalgebras for this will comonad on the error category. And there is a domain functor from the category, let's say the category of HDRs to back to, let's say, right, so we take this I from X, Y, this map is to X. So this is a golden declaration. So there's a more, what's the idea here? So the idea is that, okay, so imagine that I have a hyperdeformation retract I like this, and I have a map from some X primed to X. Okay, now I want to pull back this hyperdeformation retract along this map. So how can I do it? It's kind of easy. Well, I could even say, so there's the retraction here, J. This composition is the identity, and I can just take this double pullback here. Using an I prime to the J, the identity. So you can show that this is again, if this is an HDR, then this is again. It's neatly expressed by saying that this dot domain map is basically. Secondly, a category of HDRs and fullbacks and markers. Are those. I mean, both of these things can be proven like in a completely algebraic manner. I mean, you just, well, which I mean, on paper, we provide like an axiomatic setup for what it means to equip a category with a Morpath functor like this, and you can prove these things completely axiomatically based on these properties. You don't need any particular properties of simplicial sets. So that's it. Very formal case. Okay. So now getting close to the key definitions. So a mole square is a square. If you don't like the terminology, then error. So which looks like this. So where this is an HDR. This is an HDR. And this is a cofibration, and this is a cofibration. And the whole thing is written from sort of understood from top to bottom. This is a Cartesian morphism. Okay. Let me give some examples. Or maybe before I give examples, let me give one more definition. So let us say a map F, say from A to B, derived lifting property against the square of this and if okay, so if I'm given this square, and I'm given another square with F here, and I'm also given a map going across like this, which makes everything commute. There exists a map going here, which makes everything commute as well. Okay, so we'll say that this F has the right lifting property with respect to this square. If I write down another sort of commutative square like this, I will give you a map going from here to there. There exists a map from here to there, which makes sense. Okay. And the idea is that this is not going quite right, but this is the idea. So in the practice configuration, map with the right lifting property against
the triangle will be sort of the very big diagonal map.
Yeah, so okay, maybe this color is pointless, but so given all the solid arrows making everything commute, there should exist a dotted arrow making everything commute. Yeah.
Are the mode squares then morphisms of HDRs such that you have sort of two callback squares?
Yeah, so there's a morphism of HDRs from here to there.
Yeah.
It is, in a way, it is a very special morphism because it is Cartesian over this map, which also happens to be a cofibration. So in a sense, you could say mode squares are morphisms of HDRs, which are Cartesian over cofibrations. So I claim that this implies in particular that effective conflagrations. Let me try to explain why effective conflagrations are conflagrations, if we use this definition. So I mentioned that this phase map followed by that degeneracy map is an important example of an HDR situation. So this is an HDR, and this is a retraction. So there is one particularly important null square. So what we can do is we can take this combination of a phase map and a degeneracy map, such as this composition is the identity, and we can take the boundary here. So what I want to do is, okay, so this is an HDR, this is a cofibration, and then I want to take the HDR, which is Cartesian, over this cofibration. So what I do is I take two pullbacks like this, and here I have S of the star. So the square like this, we call a Born square. Why? Well, if you stare long enough at this definition, you will see that this right lifting property against this square is nothing but a right lifting property against a map. Namely, what we could do is we take this square and we can take the push out of this square, I mean, push out of these two maps, rather, and I can look at the induced arrow over here. Okay, from the push out back to this corner. Actually, so having the right lifting property against the square is the same thing as having the right lifting property against this map. Okay. So the interesting question is, if we take the push out here and we look at the inscribed map over here, what do we get? Well, it turns out that this is just a Born. Okay, exercise. It's running out of time. But another sort of interesting example is that or interesting source of examples, which also comes up in the work on like in the work on uniform conflagrations. This is characterization also of the conflagrations as those maps which have the right lifting property against push-out products of a cofibration and an endpoint inclusion. Now, an endpoint inclusion is, well, it's a phase map which becomes associated with a certain here. So this is an HDR as well, because it's a phase map. We could also take, we can use, I mean, because these HDRs are Cartesian over the codomain map, we can actually also take something like B and here. B times this interval, and we can maybe take cofibration here from A to B, and then, okay, we get this picture, and we get this interval times A here, and then we can look at at this map over here, which is the map from the push out of these two maps into this thing here. And that is precisely the push out product of this cofibration together with the endpoint inclusion. So, but the important thing is that such a square over here is also an example of a whole square. So these are important examples of mold squares, and they basically imply that, which I reckon sort of effective confibrations are like confibrations. They also have the right against that class of maps, which are products of confibrations and point inclusions. Now, okay, I'm going to give myself 3 more minutes. The real question I think to ask at this point is, but why did you define this right lifting property against the squares? Why not just sort of only formulate things in terms of right lifting properties against these maps? Now the point is that this definition here is not quite right. So we need to impose extra uniformity conditions. So we choose lifts. What we choose, so an effective configuration is a thing which comes equipped with such that for any mold square and every lifting property like this against this mold square, we choose a particular solution. And these solutions are supposed to satisfy certain compatibility conditions. And the compatibility conditions that we impose are best expressed in terms of properties of mold squares. Now, mold squares have nice properties. They are, they form a double category, for instance, right? So if I have a mold square like this, and I have another mold square like that, I can compose these 2 mold squares and I get a new mold square. If I have a mold square like this, and I get a mold square like that, I can compose these 2 things and I get another mold square. And that gives me 2 very natural compatibility conditions for these effective configurations. And we impose both of these. There's actually a 3rd condition that we also impose, and that has to do with the fact that these mold squares, I mentioned that the category of HDRs is closed under pullbacks, and that the Cartesian morphisms are stable under pullbacks as well. And that means that if I have a mold square here and I have a morphism of HDRs here, I can complete the whole thing to a cube. So I got like a mold cube over here, if you want. And if we started with the back of the face of a cube and the bottom of the cube, I can actually pull back this mold square, and the front of the cube is also going to be a mold square. And that also gives me a very natural compatibility condition for these lifts against mold squares. So we have what you could say, a horizontal condition, we have a vertical condition, and we have this kind of perpendicular condition. So in fact, the mold squares live in a triple category. And I think, initially you might think, I don't know where does all these compatibility conditions come from, but given the fact that these mold squares live quite naturally in a triple category, I think these are quite natural conditions to impose. As an interesting side note, I think is actually that actually we have 2 solutions to our problem. I think in a sense the vertical composition of mold squares doesn't really seem to be that important. For solving the problems, for achieving the goals that I listed on the beginning of the talk. One thing that this vertical condition achieves is it basically implies, after a lot of work, that the lifts against these worn squares determine all the other lifts. So in some sense, so if you have two sort of lifting, if you have one map here, two sort of lifting structures against the triple category of mold squares, and they agree on the lifts against these horn squares, then they must be identical. So that is actually kind of nice, I think, that we recover these horn squares and therefore the horn inclusions in a kind of a natural way. That is also quite useful for showing things like classical correctness, showing that the notion is actually, we can equip every, so also the compatibility conditions can be expressed purely in terms of lifts against horn squares. It becomes very ugly and very, ugly, but it can be done, and I think that is also, that is used quite in the paper, for instance, for showing that the definition is classically correct, showing that every configuration in the usual sense can be equipped with a lifting structure having all these triple categorical properties. All right, I should wrap up. So much of my time. Yes. Yeah. Okay. Thank you. Yeah.
Push the dimension down by one by saying that instead of lifting against the mold square, you lift against the push out.
Yeah.
And then instead of asking for compatibility conditions in triple category, you rephrase this in terms of compatibility conditions between the push out.
Yeah, the point is, I think that, I mean, it's possible, but it just doesn't become very pretty. I mean, these kind of horizontal and vertical and perpendicular conditions can, of course, be rephrased purely, I mean, can be rephrased purely in terms of right lifting properties against these maps, these induced maps. But it's just ugly. I mean, the conditions don't look very nice. And yeah, and I think it is more than just aesthetics. I think also this, yeah, I don't know. I mean, the triple categorical perspective is a bit much, but I think in some sense to ask for readers to be happy about and they see it for the first time. But on the other hand, it really expresses in a nice way, I think, the structure that we have. So I become a fan of using. Yeah. Oh, sorry. Okay, there are two people. No, I don't have. Okay.
I have a question.
Yes.
Yes. How far are you from having the model structure? You introduced some weak factorization systems, but then you made sure that you added the word auxiliary.
Yeah. So there's still a bit of work to do. That's the honest answer. So one thing which we should do first of all is we should actually show that the effective configurations are the right class in an algebraic weak factorization system. So that is not obvious from the way that I've stated this. It is true. We don't prove it in the paper, so it's going to be proved in another paper. The proof that we have currently is only classically correct, I think. So we need I mean, if we want to do everything constructively, we need a constructive proof of that. And our plan for getting the model structure is basically following sort of a similar path to what Nicola discussed in his previous talk, where we use Christian Sattler's paper on the equivalence extension property. Yeah, so we wanted to use this equivalence extension property, and then yeah, we basically got a bit lost in all the uniformity conditions, compatibility conditions that we had to check. So it was quite a bit of work. And it's not immediately obvious that these things work. One drawback, I think, of our approach. So I mean, the advertisement is like everything is co-vibrant, X-Count complexes are closed and exponentials array. The problem that we have the price or price that you pay. Okay, the compatibility conditions are quite complicated, and also we don't know constructively whether our effective confirmations are closed on the retracts. And that is also a bit of a problem sometimes. So we know that these algebras for the algebraic factorization system, the coalgebras become one. We need more be close to the retracts, erosion the confirmations are close to the retracts. It's not clear that effective confirmations are close to the retracts either. So sometimes people use retract arguments, which is
So I guess one way of showing that constructively it's not the case that every confirmation is an effective confirmation is by sort of factoring this through this BCP obstacle, right?
Yeah.
By result number one.
Actually, yeah, exactly. Yeah, no, exactly. The BCP result implies that.
Yeah.
Constructively our notion.
Is there a more direct proof of this?
I haven't tried to find a more direct proof.
Because my other question was going to be, I think Andreas Plus asked you this maybe a year ago or something.
Yes.
This
Maybe you did.
whether there is like a, whether you can, because the BCP one is like it is a cryptic model, right?
Yeah.
Showing that it can be.
Yeah.
But you could also maybe get like a constructive taboo from this.
Yeah.
But I'm guessing the answer is no. You haven't
No,
looked
I
into
haven't
this.
thought about this. No.
Okay.
You remind me that. So I got this question. No, I don't know. It would also be nice to know that, for example, disclosure on the retracts is not constructively provable. That would be my guess. But it would also be nice to have a proof of this, and that we actually know for certain that that's not.
You can stop looking.
We can stop looking. Yeah, exactly.
So you do expect that you can put these into a model structure.
I still have hope. Sure. I'm optimistic. No, I mean, I don't know. It's I have no reason to believe that it is impossible. It's not a very optimistic statement.
It's a very non-constructive.
I should ask if you hope.
We're still hopeful. We're still working on it. No, I think this equivalence extension property is a bit nasty. Yeah. I do expect that they will form the right class in algebraic characterization system also constructed.
Extension property, one squares to the morphisms of fibrations, right?
Yeah.
So
I know.
For Berg and others, they have this alignment.
Yeah, I know. No, and actually, I think that may be the only place where they actually use the fact that the cofibrations are locally decidable to get that alignment to work. So far, we haven't used the fact that the cofibrations are locally decidable. It's never really been used. I mean, there still could be anything. I mean, it should be close in the pullbacks and that's some other properties. No, I mean, in some sense, the theory is the way we have things now. I mean, we're still very flexible actually as to what the cofibration will be. But it would be nice if everything would be co-founded. Okay, we should have a break until 4 o'clock.